let's talk about low discrepancy series. What we have been talking about so far is random sampling. This means that I have a random number generator, it generates samples, and this is the sample that I'm going to use. And many mathematicians were thinking that we could perhaps do much better than that. Because what I would be looking for is a hemisphere, and I would be shooting samples on the surface of this hemisphere. I would create unit vectors on the surface of this hemisphere. And I could do this deterministically. What if I have an algorithm that doesn't generate random numbers, but it will make sure that this hemisphere, if I have 100 samples, the samples are well distributed on this hemisphere. And if you do this, you may get much better convergence and much better looking results. So below, you can see a random number generator, generated samples in 2D. And up there, the Halto sequence, which is called a low discrepancy series. What this means is it's not completely random, but it tries to fill the space reasonably uniform. Now this is not trivial. If you read after it, what you would think is that you would just get a grid. In 2D, it would be very simple to get a grid, and just put points in the grid points. And then you would have samples that are really well distributed. And this you can do in 2D. This you can do in 1D on a line, just evenly spaced out. This works there. But there are mathematical proofs that tell you that this is absolutely terrible in higher dimensions. So if you have higher dimensional spaces, then this is not well stratified. So the most commonly used sequences are the Halto series, the Sobol series, and the Corput series. You can do this low discrepancy sampling in many different ways. And this not just gives you an even-ish distribution of the noise, because you are sampling these hemispheres in a reasonably stratified way. So it cannot really be that one side of the hemisphere is sampled almost exhaustively and the other one is completely neglected. So you would get images with a noise distribution that's better for your eye. So that's a plus. But what is even more important is that this is deterministic. So if you're rendering an animation, imagine completely random sampling. You have frame number 1, you distribute your samples, then comes frame number 2, and then you distribute your samples in a completely different way. So the noise would look like this on frame 1 and that on frame 2. Completely different. So until you have converged perfectly, you will have these issues that we call temporal flickering or temporal coherence issues. Because the noise looks like this on frame 1, looks like that on frame 2, and if you play 25 of these frames every second, or maybe even more, then you will have a really disturbing flickering effect. You are computing different things in every frame. And the Sobol series and all low discrepancy series help you with that. So they love to use this in the industry because of this reason. Because in the subsequent frames, you will compute the very same thing. Advantages, okay. Disadvantages. Well, the disadvantages are also huge. It's often not trivial to implement such a thing. If you take a look at this image, these walls are not textured. These are one color green. This is a one color green diffuse wall, and this is a one color red diffuse wall. This shouldn't be rendered like this at all. This is a buggy image. And I have implemented the Halto sampler, and the problem that I encountered was called correlating dimensions. And this is a serious problem that you can encounter. I will not go into the details, but you just mess up with one small detail and you can get an image like that. Well, this is actually a delightful way of failing. I don't know about you, but most of my programming errors and these calculations don't look like this. They tend to look like this. So I usually read segmentation fault and stuff like that. So it's, if you make a mistake in global illumination rendering, even your errors might look better than in other fields.